welcome to my new video. Today we discuss about the residue. In my last video, you also know, when we discuss about the singularities and pole, the last step is the residue. So what is the residue and how we can find out these residue? So for the residue, we can say when the coefficient of z minus a inverse, means if we talk about the principal part, then the coefficient of this term means 1 upon z minus a, and its constant coefficient in the expression of fz is called the residue at z equal to a singularity, correct? Or I repeat, the coefficient of z minus a inverse in the expression of an analytic function fz around as isolated singularity called the residue of fz at of fz function at z equal to a. Clear? So now residue also can given by, I can rewrite this, residue of fa is given by 1 upon 2 pi iota curve integrated for fz dz. Clear? Or we can say the integration of fz dz is equal to 2 pi iota residue of f at a point. So both are same. So this is the formula for finding the residue by the integration. So we can expand this as residue theorem of integral. What is this theorem? First I describe that theorem also. So if fz is any analytic function in a closed curve C, if this is any curve or closed curve C, except at finite number of singular points within the C. So within the C there are finite number of singular points, then this is given by the sum of the all residue at singular point within C. I rewrite the residue theorem. So it gives by integration of C fz. So I will give you the some formula for it. To A. So for example, now we discuss with one example. I will explain there one example. If I have a question, find the residue at function fz equal to z square upon z plus z square plus a square at its pole. Clear? So what is the question? Find the residue of function fz is given by z square upon z square plus a square at its pole. So for first step we have to find the pole. For pole, finding the pole, we can make denominator equal to 0. So step 1, solution. Z square plus a square equal to 0. So it gives two poles, z plus a, z minus a. So it gives z equal to plus minus a iota. Clear? So one pole is plus iota, another pole is minus iota. Now we can, these are the simple poles of C, order 1. Then we can proceed with this formula. So residue at f equal to a iota is limit z tends to a iota function is z square plus a square, and in front z minus a, so z minus a I. At the place of a, our pole is a iota. Now again denominator we can rewrite limit z tends to a iota, numerator has z minus a iota into z square, upon denominator we can expand, then z plus a iota and z minus a iota. Now z minus a iota cancel, then what is remaining, z square upon z plus a iota. Now limit, when we existing limit we can apply, then it gives a square iota square, so it gives a square iota square is minus 1 upon a iota plus a iota. A iota plus a iota is 2 a iota. Clear? 1a cancel with a. So what is remaining? Minus a upon 2 iota. Now we can remove iota from the denominator. We multiply iota in numerator and denominator. So now next step, what it becomes? Not negative. So it becomes a iota upon 2. Clear? With this iota square minus and this minus, it will becomes plus. Clear? So at z equal to a iota, residue is given by half of a iota. Similarly, for residue at negative a iota, residue at minus a iota, if you calculate with this formula, it gives by minus a iota by 2. So residue at positive, residue at plus a iota is a iota by 2, residue at negative side, residue at minus a iota pole is minus a iota by 2. Next is the when fz has pole of order more than 1, means not a simple pole, then how we will proceed, let us see. As n at z equal to a, then residue can calculate with two formulas are there. You can proceed with any one of the formula. First one is residue of fa is equal to 1 upon n minus 1 factorial bracket d to the power n minus 1 by dz n minus 1, means d can differentiate with respect to z how many times? Less than the order n. 1 less than, if order is n, then you have to differentiate n minus 1. If order is 2, you have to differentiate 1 time. If order of pole is 3, you have to differentiate it 2 times. Z minus a to the power n fz. The second method is put z equal to a plus t in fz. At the place of z, we can put a plus t because our pole is a. Then expand the fz in the power of t, and the coefficient of 1 by t gives the residue at z equal to a. So we can approach one example with both the method. First I will show you how to use this formula with one example. So my example is find residue at z square minus 2z upon z plus 1 whole square z square plus 4 at all its poles in the finite plane, at all its poles in C. C means whatever the given plane. So our question is find residue at z square minus 2z upon z plus 1 whole square z square plus 4 at all its pole in the given region. So step 1 same for finding the pole, we can make denominator equal to 0. So first one is z plus 1 whole square equal to 0. So z plus 1 whole square equal to 0 gives z equal to minus 1 is the pole of order 2. Clear? Because power is 2, its repeat time is 2. So pole of order 2. Next, z square plus 4. So z square plus 4 we can write z plus 2 iota and z minus 2 iota, similar like our previous question. So we have two simple poles, one is z equal to plus 2 iota, another is minus 2 iota. So we have pole of order 1, or we can say simple pole. Clear? So now we have both types of pole. Two poles are simple, one is the order of 2, more than 1. So for the calculating residue of z equal to plus minus 2 iota is the same residue at z equal to 2 iota. If we can calculate residue of f at 2 iota, so what limit z tends to 2 iota, z minus a iota, sorry, a is our 2, z minus 2 iota fz. So z square minus 2z upon z plus 1 whole square upon, we can break this bracket when we break, z plus 2 iota and z minus 2 iota, z plus 2 iota and z minus 2 iota. So we can easily cancel this with z minus 2 iota. Next is we can substitute z equal to 2 iota in given function. When we substitute z equal to 2 iota and simplify it, we will get the value is 7 plus iota upon 25. Clear? So this is the residue at z equal to 2 iota. Similarly for negative part, at 2 iota is given by 7 plus iota upon 25. Next, residue at f equal to minus 2 iota, when we substitute in the formula and calculate, it comes 7 minus iota by 25. Now last is the second step where the order of pole is more than 1. So z equal to a residue at z, what, f z equal to minus of 1, because this is the order of pole is 2. So what is our formula becomes, we will see once again. Formula is this, 1 upon n minus 1, n is the order of pole. So for our case order is 2, so 1 upon 2 minus 1 is 1, 1 upon 1 is 1. So it will be, we can omit this. Next, d to the power 2 minus 1, so it becomes d to the power 1 only. So it becomes d by dz, z minus a to the power n. A is the pole, so our pole is minus 1 and order is n. So we can write z minus of 1. Clear? Then minus of minus 1 become plus 1. Order n, order is pole 2, fz. Our function is z square minus 2z upon z square plus 1 whole square z square plus 4. So this cancel out. Now remaining term z square minus 2z upon z square plus 4 we can differentiate one time with respect to z. So for differentiating we can use the formula u by v. When you will differentiate formula u by v, then we will get the result, and after that we can put z equal to 1 at the end. Here also I forget to identify that at the end you can put z equal to a. So here at the end when we differentiate it, we can put z equal to minus 1. When you differentiate it, it will comes like 2z square plus 8z minus 8 upon z square plus 4 whole square. In u by v, when we v square and then u dz by dz of v minus v d by dz of u, then we will get at the, now we can put the value z equal to minus 1. When you put the value, we will get the result is minus of 14 by 25. Clear? Hence the residue at simple pole is given by this. Next residue at simple pole given by this. Next residue at double pole given by this, or more than order is given by this. Now the last question where we can find the residue with that formula. When replace the residue with, replace the z equal to a plus t. Now I can work on this formula. So let us proceed. Residue of fz, where fz is given by e to the power z cos x square z at all its pole in the finite plane. So first step we have to find out its pole. So for pole we need the denominator. So we will rewrite the function solution. Our fz is given by e to the power z upon sine square z. Is this okay? Because cos x z is 1 by sine z. So I put into down. Now denominator make equal to 0. So when we make sine square z equal to 0, so value of sine is 0 for all n pi value, and order is 2, because if we can say this is sine z equal to 0 2 times, repeat 2 times, so it is the pole of order 2, pole of order 2. And what is the pole? Z equal to m pi, where m equal to given by 0 plus minus 1 plus minus 2 and so on. So pole of order 2, and which pole? Z equal to m pi is the pole of order 2. Hence z is not any limit point, so z approaches to infinity, so it is a non-isolated singularity. Next we want to find the residue. For find the residue we approach for the second formula. Put z equal to a plus t. A is pole, so pole is my m pi plus t. So everywhere I put z is m pi plus t. So my new function f of m pi plus t is given by e to the power z. So e to the power m pi plus t upon sine square m pi plus t. Clear? So step 1, replace z equal to a plus t. So z equal to a is the pole. So our pole is m and order is more than 1. It is not simple pole. So we proceed with this z equal to m pi plus t. Now what we can separate it and we can open it, the sign series and this e to the power series. So we can rewrite again e to the power m pi constant one side and the e to the power t is the other term. Expand this in terms of t. Next is the sine square m pi plus t. So sine of n pi plus theta is always sine theta. So it becomes sine square of t. Clear? So now I will write in the expansion form e to the power m pi e to the power z, or we can say e to the power t, is given by 1 plus t square by factorial 2 and so on. 1 plus t square by factorial 2 plus and so on. Now denominator sine series have only odd terms, so t minus t cube by factorial 3 minus t5 by factorial 5 and so on with power square, because sine t have square, so sine square t. Next we can open it, so we rewrite it again. Numerator, it will becomes e to the power m pi one plus t square by factorial 2 and so on upon, if in denominator I can take t square outside, if I can take t square outside, so first term will become 1, because first term is t and power is 2. So when t taking outside, it will become t square. So 1 minus t square by factorial 3 and so on whole square. Now I rewrite all in the numerator. So e to the power m pi upon t square 1 plus t plus so on, and it goes up 1 minus t square by factorial 3 plus to the power minus of. Clear? Now when we multiply it, then the coefficient of, we need the coefficient of t. Clear? So coefficient of t is given by first term. When we multiply, this will becomes 1 to 1 gives 1, no coefficient of t. Then this second term multiply with this one, it gives t. Clear? When this t multiply with t square, it gives 1 by t. So its constant coefficient is 1 only. So coefficient of t is e to the power m pi into 1. Hence residue at m pi is given by e to the power m pi. Clear? That's all for today, how to find the residue. In my next lecture, we will discuss the integration formula for residue. Thank you very much.